continue with section 2.4, where we want to be able to find an algorithm to get an inverse of an of a matrix if it exists. Right. So we're going to look at example 2.4.8, which will give us some ideas that we will then generalize to any n by n matrix. So example 2.4.8 says we determine whether or not the matrix A, which is 1, 2, 3, minus 1, is invertible, and find its inverse if it exists. So what we are trying to do is to determine whether or not there exists a matrix B, sorry, uh, which is B11, B12, B21, B22, such that AB is equal to I is equal to the identity matrix. Now, AB will be, if we do the matrix multiplication of A and B in that order, then we will get B11 plus 2B21, B12 plus 2B22, 3B11 minus B21, and then 3B12 minus B22. So therefore the matrix equation AB equals to I is equivalent to systems to two systems of equations that are below here. So if you look at it, you will see that the first system will correspond to basically B11 plus 2B21 is equal to 1, and 3B11 minus B21 is equal to 0. That will be a system in B11 and B21. And then the second system will be B12 plus 2B22 is equal to 0, and 3B12 minus B22 is equal to 1. And that will be the second system in, so the unknowns will be B12 and B22. Right, so those are the two systems that we have there. So we've got this system and then that system, right? So in my matrix form, these two equations are given by, so if you write it as a matrix like that, we have A uh, times B1 is equal to E1, and A times B2 is equal to E2. So that is supposed to be E2 there. Right. So what is B1? B1 is B11 and B21, right? And then in this case, B2 will be B12 and B22, right? And E1 obviously is the vector 1, 0, and E2 is equal to the vector 0, 1, right? So because these two systems have the same coefficient matrix A, the same series of row operations can be used to solve the two systems. So we've got two different systems and they have the same coefficient matrix. So to reduce it to echelon form, we need the same series of row operations, right? So we therefore perform Gauss elimination on a single augmented matrix, right? So the single augmented matrix will look like that. So instead of having uh, A slash E1 and A slash E2, we are going to have a combined one where we have got A and then E1 there and then E2 there. Since we are going to do the same row operations for E1 and E2, right? So instead of having it like that, we are going to have it combined. Since we are going to do the same operations, it will save us some space and some time to do it that way. It becomes more convenient. So we have a new augmented matrix which looks like this. And so if we perform the elementary row operation, so when we perform the elementary row operation, we will also extend it to this side, right? So in this case, we are not going to do it. We'll do an example later. But for now, uh, you can go and verify that if we perform the elementary row operation, so the operation that makes this a 0 and possibly this a 1, and then that will make that one a 0, will give you something like this. So you can verify, you can do the elementary row operation. So in the end, we are left with I is row equivalent to I times some matrix there. Now, if we go back to what we know is, if we have done that, what we have is we have got two separate systems, A E1 and A E2, right? So what it means is, so B1 will be equal to that. We remember B11 and B21, and then B12 and B22, right? And so what it means is the matrix B would be B1. Remember, we'll have B11, B21, B12, B22 will look like. So the B that we get will look like this, which is B1 and B2 like that. So the matrix B is a solution of the equation AB, which is equal to I. And by the theorem that we did in the previous video, we know that if this is satisfied, then A is invertible and the inverse of A is equal to B. Right. So what we have seen in this scenario is, if AI is equivalent, AI is row equivalent to A inverse, right? And the converse is actually also true, that if AI is row equivalent to IB, then I is invertible and the inverse of A is actually equal to B, right? So that is that. So we have a few ideas that we are going to now make concrete in the form of a theorem. So suppose we've got a matrix A, which is an n by n matrix. Then A is invertible if and only if there exists a matrix which is an n by n matrix B, so that AI is row equivalent to IB. And in this case, the inverse of A is equal to B. Right. So suppose that AI, so we are going to do that. We're going to look at the two statements. Suppose AI is row equivalent to IB for some matrix B, and then let B1, B2, Bn denote the columns of B. So you remember the notation that we introduced in the previous video, where this will be column 1, column 2 up to column n, and E1, E2 up to En denote the columns of I, right? So this will be column 1 of E1, column 2, sorry, column 1 of I, column 2 of I, up to column n of I. Then AE will be row equivalent to IBJ, right? So we are just here, and so if we take, instead of having the I, remember what we did in the example here. If we take AE2, we are going to get B2, right? If we take AE1, we are going to have B1 on the other side, right? So that's what we are just talking about here. That if we say AEJ, it will be rho equivalent to IBJ for every column of uh, of B, right? So therefore, according to theorem 2.3.6, ABJ is equal to EJ, right? So if this happens, this is what it means. ABJ is equal to EJ, and this is for every column. So therefore, theorem 2.4.6, which tells us about an convenient way of writing the product of A and B, we know that AB becomes AB1, AB2, ABN, where AB1 is column 1, AB2 is column 2, up to ABN, which is column N. And this is just, there's some brackets missing here. This is just E1, E2, up to En, so the matrix that, but that is just I. And by the theorem that characterizes invertibility, we know that if this happens, if AB is equal to I, then A is invertible, and the inverse of A is equal to B. So that needs to be fixed. A inverse here is going to be equal to B. Right. And so that proves the one part of the theorem. The converse is left as an exercise, and it's exercise 2.4, number 8 in the textbook. Right. So what do we know now? So theorem 2.4.9 provides us with an algorithm to determine the inverse of a matrix uh, A, if it exists. So what do we need to do? We need to perform Gauss elimination on the augmented matrix AI, and if for some matrix B, AI is rho equivalent to IB, then A is invertible and the inverse of A is B. And if AI is not rho equivalent to IB for any matrix B, then what it means is A is not invertible. Right. So now we know how to find uh, the inverse of a matrix. We found an algorithm in theorem 2.4.9, and so we are going to look at some examples to see how we can do that, how we can use the algorithm. So the first example is, so here it's supposed to say do example 2.4.10. Right. So you are supposed to do 2.4.10. We are going to look at 2.4.11. Right. So it says let A be equal to the matrix 1 0 minus 1 minus 1 2 1 0 2 0. So we determine whether or not A is invertible and give its inverse if it exists. How do we do that? Well, we start off with our AI, and that is equal to, we put our A there, and then the 3 by 3 identity matrix. Now the first step is to make sure that we have a 0 here. We want to reduce it to echelon form first, right? So we have R2 goes to R2. So here for us to get a 0, we want to say minus 1 plus 1, right? So in other words, R2 goes to R2 plus R1. So we get minus 1 plus 1, we get a 0. 2 plus 0, we get a 2. And then 1 minus 1, we get a 0. And then 1 plus 1, we get a 1. 1 plus 0, we get 1. 0 plus 0, we get 0, right? Now we go on to the next elementary row operation. So here, as you can see, we want this value to be a 0 also. So anything below 2 should be 0. So if we do that, how do we do that? We can just say 2 minus 2. So we can say R3 goes to R3 minus R2. So 2 minus 2, we get 0. So in fact, we start here. 0 minus 0, we get 0. 2 minus 2, we get 0. 0 minus 0, we get 0. And then 0 minus 1, we get minus 1. 0 minus 1, we get minus 1. 1 minus 0, we get 1. So we have that. Now this system is in echelon form, and at this point we can see that because we now have zeros here, there's no row operation that will make this value a non-zero, right? This entry can't be a non-zero, and because it can't be a non-zero, we can't get the identity matrix, because remember, the identity matrix will have non-zeros here. That's one of the conditions. It will have 1 1 1, and in this case we have zeros here, so we are not going to be able to find any elementary row operation that will make this a non-zero, but leaving these ones as zeros. So in that case, we know that AI is not row equivalent to IB for any matrix B. So therefore, by theorem 2.4.9, the matrix is actually not invertible. So we have looked at an example. So you see that example 2.4.10 is an example of a matrix that has an inverse. So you will be able to find it. So you can do it and see. But this one doesn't have an inverse, and this is because we get to where we have zeros here, and then therefore we can't have I on this side, right? Let's look at another example. So we looked at one where it was not invertible, and I say that example 2.4.10 is an example of a matrix that does have an inverse. So you you need to look at that. So consider the matrix A, which is 1 0 minus 1 minus 1 2 1 minus 1 4 2. So we determine the inverse of A if it exists and use it to solve the system AX is equal to B. So we've got two questions. One is determine if this is invertible and find its inverse, and also if the if it's invertible, use use that inverse of A to find what would be the solution of AX is equal to B. So we start off with our AI, and we put our A and then the identity matrix on that side. And the first step is anything below 1 should be 0. So that one is a 0 already, but that one is not a 0. So we say minus 1 plus 1. So R3 goes to R3 plus R1. And if we do that, we end up with something like this. You can do the arithmetic. And then when we get here, we want whatever is below 2, the diagonal entry here, to be 0. So we want 4 to be 0. How do we get that? We can say 4 minus 2 times 2. So in other words, R3 goes to R3 minus 2R2, right? That is the row operation there. And then if you do the row operation, 0 minus 0, 4 minus 4, 1 minus 2, you get minus 1, and so forth. You do it you do the same on this side, and we get this, right? Now when we get here, the next step is to make this as 0. So now we've got non-zeros in the diagonal, we can make this a 0. How do we make it? We use this one, right? So when we want to make zeros this side, we use the the diagonal, the rows. We use the row on top, right? If you want to make a 0 here, you use this. If you want to make a 0 there, you use this. If you want to make a 0 there, you use this. But when you want to make a 0 here, you use the diagonal entry here, the one that is below. When you want to make a 0 there, you use this one again, right? And so forth. So in this case, so we want to make this a 0. How do we do that? We say R2, so we say 1 1 plus minus 1, right? So in other words, R2 plus R3, and that is the row operation there. So if you do it, you will get your 0 there, and then you do the row operation on this side again. Now the other thing is we want to make this a 0. How do we make it? We have to say minus 1 minus minus 1, right? And then so that becomes R1 goes to R1 minus R3. So we're saying minus 1 minus minus 1, and we get, so that is the row operation. And if we do it, you will get your 0, your desired 0 there. So now what is left is to just make the entries in the diagonals 1, right? So we could have, so when we got here, we could have decided to make them 1 before making this a 0 and that a 0. It doesn't really matter which you do first, right? So you could have decided to say, okay, I'm going to divide R2 by half, and then R3 by minus 1, and then you'll have ones, and then you can then make this a 0, make this a 0. Or you can make this zeros, and then here now we then make this a 1, make that a 1. How do we make that a 1? For us to make it a 1, we just have to say R2 goes to half R2, right? That's an acceptable elementary row operation. And then here when we want to make it a 1, we will say R3 goes to minus R3, and then that becomes 1, right? So therefore, and then we do this. So we do that, those row operations again on this side, and we are left with that. So now we've got I there and a B there, and then we know that whatever is here will be the inverse of A. So therefore, according to theorem 2.4.9, A is invertible, and A inverse, that's supposed to be A inverse, is equal to that. And that completes the first part of the question. Now let's look at the second part. So by theorem 2.4.7, the system AX is equal to B has a unique solution. Now for a vector X in R3, AX is equal to B if and only if A inverse AX is equal to A inverse B. And that is just equivalent to saying that, so if you look at this side, what we are just saying is this is equal to X, because A inverse AX becomes IX, which is X. So X is equal to IX, which is equal to A inverse B, right? And so we then use the inverse that we found here. We multiply it with B, and we get 403. So that becomes our solution, the unique solution. Let's look at another example to see how we can use this idea or this algorithm of an inverse to solve some different type of questions. So we want to look at example 2.4.13. So let A be equal to 121 010 132. So we want to find all matrices B such that AB is equal to A squared plus 2A, if any exists. So if there are some matrices B that will satisfy this, right? So if A is invertible, then a 3 by 3 matrix B Then for a 3 by 3 matrix B, AB is equal to A squared plus 2A if and only if. So if it's invertible, we know it as an inverse, and we know that this will be equal to that if and only if we can multiply by n inverse throughout. So if we do that, we say A inverse times AB, and then here we say A inverse times, here we had said A squared, but A squared is just AA, so we can write it as that, plus 2A inverse A, right? And this is true if and only if, well, if that goes away, we get B, and then there we get IA, which is just A, and then here we've got 2 times A inverse A inverse A is just I. So in other words, B would be equal to A plus 2I. But this can only happen if A is invertible. If A is not invertible, we pretty much can't do anything, right? So what we need now to find is uh, we need to determine if A is invertible. If A is invertible, then we know what B will look like. Right. So we have our AI. We want to find the B such that we get IB, right? Or whatever we call the inverse. Here we have used B, so we can't really call the inverse of A B in this case. So we can call it anything else, C or whatever. Right. So we have our system like that. So we start off with, we've got 1 there, we want a 0 there, so what do? We say 1 minus 1, so we have R3 minus R1, right? So that is our row operation. We do that, and then here we've got 1 1, we want this to be a 0, so we say 1 minus 1, so R3 minus R2, and then we get a 0 there, and then we are left with that. And now we have diagonal, and it's 1, so that's good. Now we want to make this a 0. We use this, so we say R1 minus R3, right? And then that is our row operation. We do the row operation everywhere, and we get our 0 there, and we are left with this. So for us to make this a 0, um, we use this row to make this a 0. So we say so we are here, we say R1, so 2 minus 2 times R1, sorry, 2 times 2 times 1, which means we are saying R1 minus 2 times R2, which is the row operation there, right? And then after that, once we do that row operation, we are left with that, and therefore this is the inverse. And what it tells us is A is invertible. So because A is invertible, the unique solution of B, which we had calculated, well, which we sort of knew already to be B is equal to A plus 2I. So therefore B is equal to A plus 2I. And if you do the arithmetic, you will find out that that is equal to that. Thank you. That is all for section 2.4.